should I?
Good afternoon. My name is Valeria Villegas, and this project explores the metallicity of RR Lyrae stars, particularly those found by the Sighting Spring survey. This is a survey that was ongoing for about 9 years, so it collected quite a bit of data. So, what is an RR Lyrae star? It's classified as a pulsating intrinsic variable star. Variable because its brightness changes with a known period, typically 5 hours to 15 hours. Intrinsic because these changes in brightness are actually due to changes in the star itself, as opposed to a perceived change due to light bending or obstruction of some kind. So they are really, really common stars among our galaxy. In this image, RR Lyraes are found within the major disk, also in the halo region, and in the clusters as well. Since they are so abundant, and since we understand their pulses and brightness duration periods, they make really great standard candles, which serve as a galactic milepost, kind of like a physical distance indicator based off of light. So what is metallicity? Metallicity in astronomy is anything heavier than helium. So any element that is not hydrogen or helium is considered a metal. And for a star, we determine its metallicity by comparing it with the metal content of the sun on a logarithmic scale. So a metallicity of 0 means that that star has a metal content equivalent to the sun. -1 would mean its metal content is 1/10. -2 would be 1/100th. Why is it important? So through metallicity, we can determine the composition of the star, and since it is such a common star in our galaxy, this would also give us further insight to our Milky Way. Furthermore, through the composition, we can gain insight as to when and where they were born. But most importantly, since they are used as standard candles, this can help improve calculations for their physical distances, allowing us to better map our galaxy. So here we have an image of the Sighting Spring Observatory. This is right there is the Polishschmidt telescope with the dome closed. That's responsible for all of the measurements taken. An interesting fact about this telescope is that it was actually the first to have captured an image of Sputnik in 1957. Since the update, though, it was fitted with a spherical mirror of about 1 meter in diameter, which is really huge if you think about it. And so because of that, it's able to have a larger field of view as opposed to the parabolic mirror. So this is the Polishschmidt with the dome open. So where are we looking? Here we have the celestial sphere, and within the Sighting Spring survey, which primarily focused on the southern hemisphere, I decided to take a subset of that with these particular coordinates. So declination can be thought of as a celestial latitude, whereas right ascension can be a celestial longitude, to give you kind of a familiar perspective. Okay, and here we have the galactic sphere, the celestial sphere with its constellations, and that little yellow rectangle is the subset that I particularly focused on. So in this project, I used Excel to sort and arrange the data. The metallicity was taken from 10,543 RR Lyraes in the galaxy, and I created a histogram to find the average metallicity. Then I focused on that little yellow square and sorted these stars by their distance to the sun and plotted their corresponding metallicities based on the distance group. So here we have the histogram of the average metallicity. As you can see, it came out to negative 1.39, which means that it does in fact have a lower, that your common RR Lyrae star has a lower metal content than that of the sun, pretty significantly lower. However, the really interesting part is that as we plotted the metallicities against increasing distance from the sun, which is also just a reference point, really we're looking at the galactic plane. There's a very obvious drop here. So here we can see that the slope of that is negative 0.016, whereas here negative 0.0208. So what that tells us is that at this point, approximately 22 kiloparsecs away from the galactic plane, we have a change in ratio in metallicity of approximately 1.29 actually, which tells us that the metal content of the stars farther away is much lower than stars closer to our galactic plane. Here is the slice of the survey, and this darker region is where we have that change in metallicity. So, to conclude, we have determined that the average metallicity of an RR Lyrae is negative 1.39, but this ratio difference is what really gives us insight into what the galaxy looks like at farther distances. So the next question is, where did this is an indicator of a different composition, but why? Astronomers have found differences in metallicity closer at about 1.6 kiloparsecs from the galactic plane, but as far as I'm aware, nothing close to the 22 kiloparsecs. So potential reasons could be changes in temperature, changes in energy. Really, that would be the next question in answering. But at least for now, we have a better understanding of the composition of these stars, which make up such a large portion of our galaxy, and now we can have a better understanding of the galaxy as a whole, since they are such a large component. With the remaining time, I'd like to take a moment to thank the School of Science, Math, and Engineering for allowing me to present my findings, and Professor Barnes for his support and guidance throughout this project. And thank you for your time. Yes, please, questions. Well, I let the telescope do all the hard work, but it really was data that was already available, and I imagine that so with the RR Lyraes, since their variability is due to the change in radius, so I don't think that we can focus on the wavelength particularly, but the calculation for the metallicity is something that was already just kind of embedded in that data. Yes. Yes. If the stars were closer, we could certainly do a spectroscopy analysis and take a look at the wavelengths. However, when we're looking at distances so far away, I mean, 1 kiloparsec is over 3,000 light years. So when we're looking at those distances, really all that matters is if it's heavier than helium, because that's kind of what we can figure out. But interestingly enough, since we did find such a change in metallicity, that kind of gives us insight as to what the galaxy could have looked like in its early years, since it tends to be an older region. Stars in that area aren't as metal dense, and so tend to be older. Any further questions? Great. Thank you.